All right, hey everybody. So today we're going to start looking at matrices, and we're going to spend a little bit of time here working on the matrices, and then we'll see how matrices can be applied to systems and can be a really helpful tool for us. So we're going to look at some matrix operations today: adding, subtracting, scalar multiplication, and multiplying matrices themselves. But let's just talk about a couple basics before we get started. So a matrix is an arrangement of numbers. We call each of these elements into rows and columns. And when we talk about the dimensions of a matrix, we always talk about the dimensions of the matrix as the number of rows by the number of columns. So when we look at both of these matrices, so one is a matrix, two matrices, right? So singular versus plural. When we look at these two matrices, we look at them and we say, okay, how many rows do they have? They have 3 rows. And how many columns do they have? They have 2 columns, so this would be a 3 by 2 matrix. Okay, so just a little bit about that dimension stuff, and that's going to be important a little bit later on. So like I said, each number is called an element of the matrix. We can talk about their dimensions. We name matrices with capital letters. So notice this is a capital A, that's this matrix, and a capital B is that matrix. So let's do some operations here. Matrix addition, really simple. If I'm going to take matrix A plus matrix B, all we have to do is add the corresponding elements. So I look at this top left element, and I look at the top left element in the other matrix, and I add those together. 2 plus 0 is 2. Okay. Then we go to the top right, and we say, okay, we're going to do 1 plus 1 is 2. Then we come down here, 4 plus 3 is 7. 2 plus 5 is also 7. 3 plus 1 is 4. 0 plus 6 is 6. And the resulting matrix is this one. Okay. Now, when we look at that, okay, we had a 3 by 2 matrix and a 3 by 2 matrix. When we add them together, we get a 3 by 2 matrix. We can only add matrices when they have the same dimensions, right? Because we're adding corresponding elements. If this was like a 3 by 3 and there was another set of numbers over here, there wouldn't be anything to add the 7 with from that matrix, so we wouldn't be able to do it. So just keep that in mind, that to add matrices, they have to have the same dimensions. All right, let's subtract some matrices. Okay, so now we're doing B minus A. Now subtraction is the same as adding the opposites. It's just addition. So we're taking the elements in B, subtracting their corresponding elements in A. We've got 0 minus 2 is negative 2. We've got 1 minus 1 is 0. We can work our way through the entire thing. 5 minus 2 is 3. 1 minus 3 is negative 2. 6 minus 0 is 6. There we go. All right. Now, take a look at what's different in this one. Okay, here we're going to find 2a plus b. So let's focus on the 2a first. Okay. This would be what we call scalar multiplication with matrices. We need to take matrix A times 2. And scalar multiplication is really easy. We're just going to multiply each element by the scalar, by the 2 in this case. So 2a would be, let's take each element in A and multiply by 2. So it becomes 4, 2, 8, 4, 6, 0. So we do that. Then we're going to add on matrix B, which we are not multiplying by 2. There's no 2 in front of that. Sorry for the sloppy writing there. We're just following out order of operations. We know we need to multiply before we add, so that's why we did our scalar multiplication first. Now we're going to add on the B, so now we can just add these two matrices. They're still the same dimensions. And what do we get? 4, 3, 11, 9, 7, and 6. And that's what we have. So there's addition, there's subtraction there, and scalar multiplication. Now let's get to how do we actually multiply two matrices together? How do we take matrix A times matrix B? And the definition for this one isn't often what students think. Students just think we take 2 times 1, we take 1 times 2, 0 times 3, 3 times 4. That's not how it works. It has a really interesting definition, but it's this definition of multiplying matrices that's really going to be helpful for us later on when we get to how we apply these to systems. All right, so this is how it's going to work. Let me make this a little bit bigger. All right, so we are taking a 2 by 2 matrix times a 2 by 2 matrix, and I'll get into this more, but our resultant matrix will be 2 by 2. So let me walk you through this. Okay, so I'm setting up my 2 by 2 matrix here, and I'm just putting in some blanks here for as we write. This is gonna get kind of colorful to try to help you out. All right, so here's how we define this. This is our top left position in our matrix. Now sometimes you'll see mathematicians label matrices kind of like this, but then they'll call this 1, 1. They'll call this 1, 2, meaning row 1, column 1, row 1, column 2. This would be row 2, column 1. This would be row 2, column 2 to describe their position. I typically don't do that unless I really have to. I think we're going to be fine without it. Okay. But if I want row 1, column 1, I take row 1 in the first matrix, and I take column 2 in the second matrix. Excuse me, row 1 and then in the first matrix, column 1 in the first matrix. Or like I just like to call this is top left. So I'm going to take the top row in the first matrix times the left column in the second matrix. Now how do I do that? Well, I take 2 times 1. 2 times that 1. Then we add 1 times 3. And that's how I get that spot. Now when we go to our next location, let's go to the top right. Top right is going to be top row times right column. And when I say we're taking a row times a column, how do we do that? We take this 2 times that 2 plus this 1 times that 4. Let's go to our next position. Bottom left, bottom row, left column. How do I take the bottom row times the left column? 0 times 1 plus, it's always plus, 3 times 3. Okay. And lastly, we've got bottom row, right column for the bottom right spot. 0 times 2 plus 3 times 4. Okay. Now, I can't show you this, but usually when I'm doing this and I've got it on the paper in front of me, I'm usually using my fingers and I'm like matching up. I'm saying, okay, 0 times 1 plus 3 times 3. 2 times 2 plus 1 times 4. And I just kind of do this finger pointing pattern here to make sure that I pair them up. However you guys can do that and keep that straight is up to you guys. Now let's just figure out what do we have here. So our top left is going to be what? 2 plus 3, which is 5. Top right is going to be 4 plus 4, which is 8. Here we're going to have a 9, and here we're going to have a 12. I really like zeros when I multiply matrices. They make it a little bit easier. Okay, and this is a matrix that I get when I take A times B. Now let's take B times A. So this is just multiplication. We get the same thing, right? If I take 3 times 4, that's equal to 4 times 3. Multiplication is commutative, isn't it? Commutative meaning we can switch the order and it doesn't change anything. Well, let's see if that's really true. Now matrix B is in front. Okay, I'll write down matrix B here. 1, 2, 3, 4. I guess I was really creative when I made that matrix. Times matrix A, 2, 1, 0, 3. So this is a 2 by 2 times a 2 by 2. We're going to get a 2 by 2. Let me set this up again. All right, so let's do top left position. Top row times left column. 1 times 2 plus 2 times 0. Top right. Top row, right column. 1 times 1 plus 2 times 3. Bottom left, bottom row, left column. 3 times 2 plus 4 times 0. And bottom right, bottom row, right column, 3 times 1 plus 4 times 3. And what do we get? We get 2. 1 plus 6 is 7. 6. 3 plus 12 is 15. So this is what we get when we take B times A. Now compare that to what we got when we took A times B. They're different. So here we can make a statement, and it's a really important one for us to notice. Matrix multiplication is not commutative. Commutative. In other words, order matters. The order that we multiply the matrices really does matter. Okay, let's look at this one now. We're taking matrix A times matrix B. So let's set it up. We're going to take left row, or top row times left column. 1 times 2 plus 3 times 0 plus 4 times, 1 times 2, 3 times 0, 4 times what? There's nothing for it to multiply. Okay? We cannot multiply these two matrices. This one is not possible. Okay, so another important thing to learn is that the order of the operations of multiplication does make a difference, but can we always multiply two matrices? And the answer to that is no, we can't. We talked about when we're adding, they have to be the same dimensions, the same number of rows times same number of columns, because we just match up the corresponding elements. Well, now when we think about when we're multiplying, the number of elements in a row in the first matrix has to match up with the another number of elements in the column of the second matrix. Okay. Can we take B times A in this one? So now let's switch the order here. Let's see, is this one picture? Yeah, it is. Let's switch this order. Let's put the 2, 0 first, and then the 1, 3, 4, 2, 2, 0 that way. So now when we take B times A, let's see here, we're going to take this row times that column, and again we see an issue that this doesn't match up. We can take the 2 times 1, but there's nothing to multiply the 2 by. So here's what's going on. You can multiply two matrices only when the number of columns in the first is equal to the number of rows in the second. Okay, when we look at this, the number of columns in the first, there are 3 columns, has to match up with the number of rows in the second. Okay, and we can see that here because this has 3 columns, the 1, the 3, and the 4, all need to match up with the 2, the 0, and the something, and they don't. Okay, so here's how this works out. It's pretty slick. So number of columns in the first has to equal the number of rows in the second. So let's say the first one has R1 rows and C1 columns. Now we're going to multiply that by the second one, okay, where the number of columns in the first has to be equal to the number of rows in the second. So the number of rows here, okay, by the number of columns, these right here have to be the same. The number of columns in the first has to be the number of rows in the second. And what's cool is that your result